Okay, what do you think? So when you saw 2x minus 7 equals 0, what comes to mind? So from your math past, from your history, yeah.
Like the urge to like
Isolate x. To do what?
figure out what value for x gives you
Right. So good. So you saw that and you thought, oh, this is my instinct is solve for x, find out what x is. Okay, and that's normal, right? And it's especially from a calculational cultural world, right? Culture. All right. So, and of course, x is 3.5. So could x be 4 or 10 or negative a half? Could x be 4 or 10 or negative a half? Yes or no? Donna says no. Anybody say yes? What are you thinking? So it has to be 3.5 because of that equation. It satisfies the equation. So in light of that, in light of 3.5 satisfying the equation, could x be 4 or 10? Okay, so then it'd be a false statement. But in order for you to say that, in order for you to say, oh, it would be a false statement, then you're saying x is 4 or 10. So what if x was, I didn't tell you this before, but x is the number of hours since your plane left the ground. Then could x be 4? Could x be 10?
Doesn't it depend on how long your flight is?
Okay. Well, does it depend on how long the flight is? Could x be 200? Even if the plane is landed, could x vary for greater values after the plane's landed? According to that definition? Ashley says yes. Okay, what about negative a half? Could it be negative a half? No? There would be no meaning to x equals negative a half in that scenario. Actually, half an hour before the plane took off. Yeah. So the idea here is that we see x's as like this curtain. What's hiding behind the curtain? We've got to figure it out, right? And ta-da, it's 3.5, or ta-da, it's 2, you know? Rather than thinking of x or variables as a variable, like variables vary. They take on many values as a situation plays out or unfolds. Okay? So kind of what Sarah was saying. So yeah, x could be 4 or 10 or negative 5, and then it just makes the equation false, right? So it makes the equation false. So maybe this 2x minus 7 is like is something particular on some particular time during the flight, like maybe someone took their mask off and they threw them out the plane. Okay, and that happened at x equals 3.5 hours, and that equation was to figure that out when that happens. Okay. So x, in fact, takes on many real numbers. That's why it's called a variable. It varies, variables vary. Okay? So x equals 3.5 simply highlights a particular moment on the flight. So we define a variable as a letter notation that represents the value of a changing quantity. And this is so crucial. I mean, this is kind of like the bottom line of calculus, that calculus models the real world as quantities change in how much, and change and they vary at varying rates. So calculus without variation of a situation unfolding is very static and not really calculus. Calculus models the real world as quantities vary and at varying rates. So the variable, seeing variables as varying is crucial kind of underpinning of calculus. All right, a constant is a non-changing value no matter what the situation is. What's an example of a constant that never doesn't change ever?
Pi.
Pi.
The speed of light.
Speed of light. Good. Speed of light. Pi. So there's lots of constants like that, right? So it's the things that just never change no matter what. So then what we call a parameter is also a letter. Variables are first of all a letter or notation. A parameter is a letter that represents the value that's constant, but in a given situation, in a given context, it doesn't change. But then if you change the context, that value could change. So does the difference between a variable and a parameter make sense? Variables vary in the context you're looking at. But a parameter is set until you change the situation, and then it could take on a different value. So what about the acceleration of gravity? Is it a constant or a parameter? Acceleration of gravity. Constant or parameter? She says constant, because it never doesn't change, right? Anybody say it's a parameter? How? How could it be seen as a parameter also? So yes, it's valid to think of it as a constant. No matter where you go on Earth, acceleration of gravity is the same. Right. Go to or at like higher elevation. I think the acceleration of gravity changes if you change elevation. So if you were at the very top of a very high mountain, you might have a different gravitational constant. Or if you went to the moon or the Mars. So in that sense, it could be a parameter too. So certain things, it depends on what your kind of universe is, right? Acceleration of gravity, most of the time would be considered a constant. But if you're talking about astrophysics, well, this is a parameter now. It depends where you are, right? Okay, and so then the domain of a variable is all possible values that the variable takes on as it changes, right? What are all the possible values that variable takes on as it changes? That's the domain. The domain of a parameter is just the one value, right? So you can also talk about the domain of a parameter. Well, there's not really a domain, it's just the one value. Yeah, it's definitely not a variable. It's definitely not a variable. This is the capacity of the pond is fixed. But what? Anyone?
Almost I feel like if you change like the problem, or if it's just basically the volume of like a cylinder pool, it could like change the context.
Right. Yeah. So it's constant in this situation, but in a different pond filling situation, you could have a different capacity. Yeah. So then what is this? This is a parameter, right? All right. Pi, of course, is a constant. 5.4 feet, the depth of the pond. What do you think? And Angel and Richard, just jump in whenever.
A parameter.
Parameter. Is it a parameter? Okay, I don't know. So I didn't really emphasize this when we went over the definitions, but there's a qualification about a parameter. Do you remember?
It has to be a letter.
It has to be a letter. So what is this? It's not a parameter. It's the value of a parameter. It's the particular value of some parameter if you named it, say, D for depth. What's that? No, it would be none of the above. Right? If we go a different, no, it's not constant. Constant is a number that's never, ever changes. So if we were to go to a different fish raising pool, it could have a different depth. But a parameter, the first and foremost, it's a letter. When you assign a letter to it. So this is, it's most closely related to a parameter, but it's not a parameter because it's not a letter. So it's the value of a parameter. Does that make sense?
Yeah.
Yeah. Okay, what about R, the radius of the pond in feet? Yeah, so none. Parameters are letters, okay? But it is the value of a parameter. It's most closely related to a parameter, okay? All right, what about r, the radius of the pond? Parameter. Could change in a different situation, but it's fixed in our situation. Okay, the number of fish in the pond. Number of fish. Parameter. Careful. Doesn't have a letter.
You could give it a letter.
Well, but it doesn't have, it's not a letter there. Yeah, when you give it a letter, then that letter is the variable or the parameter. Okay? So so whether the number of fish you think of as a parameter or a variable in this situation, it's still neither of those because it's not a letter. Okay? H, the height of water in the pond.
Variable.
Okay? Variable, very good. V, the volume of water in the pond. Also variable. If I just wrote the volume of water in the pond and didn't have the V, is it a variable? No. It's the description of a variable, but it's not, the variable is the letter, okay? 32.17, acceleration of gravity. Talked about this one, right? Yeah, I think so. So certainly it's constant, but you could argue that it's also a parameter. It's like, what about raising fish on the moon? You know, like, or, you know, right? And so, yes, you could argue that that's also a parameter, but actually it would not be a parameter because it's not a letter. So if you had G equals, or G, the acceleration of gravity, then you could argue constant or parameter. Does that make sense? It'd be argued either way. Okay, 70.9 gallons per minute, the filling rate. Richard, what do you think?
None of the above.
None of the above, because
It's just a rate.
it's a rate. So what is it most closely related to? So it's value of what?
Parameter.
Parameter. Yeah, parameters are letters. But this, if we had given it, you know, m equals or m, then it would be parameter. So there's the value of a parameter, but not a parameter itself. So is this making sense? So this is like in terms of modeling situations, real world situations, this kind of having this construct for, you know, defining variables, parameters, and constants is really important to, you know, see the difference. Okay, any questions on that? All right, so I have a dynamic illustration of this. So here's an animation. There's actually one that we use in Dirac calculus. You can imagine that. You can imagine it kind of smoothly changing here, being smooth. Okay, so there's there's 5 different notations here. A, dx, left x, delta x, and x. I want you to identify these as either a parameter or a variable, and then if it's a parameter, what's its current value, and if it's a variable, what's its domain. Let's regroup. Okay, what do we think? Quickly, we got some more stuff to do here. So A, what do we think? A, variable, parameter, Yasra, what did you guys talk about? Parameter with a value of 0.5. Okay. Dx, Ashley, what did you guys talk about? Variable? What's its domain? What's the domain of that variable dx? All right, do you need to be able to read the numbers and know the domain of dx? Is it all real numbers? What values is dx? Do you see that dx is represented by this interval width? Do you see that? So what's the lowest value that dx takes on? What's that? 2, is that dx? Do you see what dx is? What is dx? Do you see that it's an interval width? It's a change in x. So at any given moment, dx is the length of the blue arrow. That's what it's trying to show you. From here to here. So what's the lowest value that dx takes on? It takes on 0, right? It starts. So when x is at left x, dx is 0. Do you see that? Right now, dx is 0. And then what's the greatest value that dx takes on? Right, do you see that the greatest that it takes on is 1.5? Because when it hits 1.5, then it starts over. It jumps over to 0 again. See that? Okay, what about left x? What about one of you guys? What did you guys talk about for left x? Angel and Richard.
So we were kind of only because it is like a certain number, but it changes.
Okay.
We said it was a variable, but then we listed the numbers that it was.
And why are you saying but? So you said it's a variable, and then if I ask you what the domain is that what you're saying the domain is when you listed the different numbers?
Yeah.
Okay.
Yes.
So I just was wondering why you said but. You said, we said it's a variable, but we listed the different numbers. Is there a conflict there?
Oh, we just didn't know if like the graph, we're supposed to go with the domain just of the animation itself, or are we assuming that if the animation continued onwards?
You decide. You decide. So either way, you back up your answer, and they could both be right. Kind of like the acceleration of gravity could be a parameter or could be a constant.
Yeah.
As long as you can back up what you're saying, then you're right. But yes, it's a variable, and it's taking on these, like, instead of taking on a continuous string of values, it takes on discrete values, but it's still a variable because it's changing. All right, fine. Or delta x. Elizabeth, what do you guys talk about for delta x? Is that a variable or parameter? Okay. Yep. So in this situation, it stays at 1.5. And so it's just showing the delta x like for right before left x, but delta x is still, this is still delta x here, and this is delta x over here. So it's always for any of those intervals between the red dots represents a value of delta x, which is always 1.5. So it's parameter. And finally x, variable or parameter? Variable, right? It's taking on all these different values. So you could say, it takes on all values x greater than or equal to a. Like, so x starts at a and takes on all values. But actually the animation, I think, starts at like 2. So you could say x is greater than 2 because you're saying I'm arguing that the animation, it starts at 2, I think. So yeah, so it actually starts at 2. But the idea of a would be that's where the value of x would begin. That's just not what the animation shows. Okay, questions on this exercise? Well, like I said, so this is down the road in Dirac, so I'm using it for a different purpose here, right? I'm using it just for us to practice variables and parameters, but there's a whole kind of conversation about calculus that we're going to have later in the course that this is about. Anybody have a question? Okay, very good. So let's talk about any questions. So here's a scenario. distance a motorcycle travels from the intersection in miles is a function of the time elapsed since leaving the intersection in minutes. Name this relationship G. Okay, so you got an idea of the situation here. All right, so I'm going to put something on the screen. I want you to listen to your reaction. Okay, so listen to your reaction. What do you think when you see this? What comes to mind when you see this? What's your internal reaction to that? Elizabeth. So you see that that's telling you how many miles the motorcycle is at 8.3 seconds. Minutes, 8.3 minutes. Agree with that? Does anyone have a different reaction to seeing that? Maybe no reaction at all? Any other thoughts that came to mind? Okay, so this is, anybody know what this is called? Just as a general term, what this notation is called? So this is function notation, right? Function notation. And so function notation, so we want to see this as kind of multiple things together as a unit, right? As a unit. And so the whole thing is the value of the dependent variable, number of miles. But the whole notation is the number of miles, like Elizabeth said. And that's the dependent variable of a function whose name is g. G is the name of the function. So is g variable or parameter? The parameter? Is g itself taking on a specific value in this situation? Is g itself taking on many values in this situation? Yeah, it's just a name, right? So it's like a label. It's not being used as a parameter or a variable here. It's just a name. It's a label. Okay. And so then it's the number. That whole thing is the number of miles when the independent variable is 8.3, number of minutes. It's function notation. Okay, I mentioned last time. In this course, my goal by the end of the course is that you would start having a stronger and stronger function mentality in terms of as a tool, as something powerful to use in expressing mathematics and for use in doing mathematics. All right, here's another one. So here's a function, 3x squared plus 8x minus 17. Boom, f of 2. What came to mind when you saw this notation? What does it mean? An output value when your input value is 2. Other reactions? Angel, Richard, what's your reaction when you see that, f of 2? There's no right or wrong answers here. I truly want you to say what was your reaction.
The value of function f when the independent variable x is 2.
Okay. Did anyone have a different reaction when you saw f of 2 versus g of 8.3? You think yours was the same? Okay. Be honest. Did this seem different to you? And you thought differently about f of 2 than you did g of 8.3?
Actually, kind of.
Okay.
The G function is like a word problem.
Okay.
Actually find units.
Okay.
But this one is a function.
Okay. Input output. Did anyone see this as something to do as opposed to g of 8.3? Or maybe you saw both of them as something to do. So is that what it is? Is it? So I think this is in our culture, in our math education culture. I think most students see this as something to do. And my question is it? Is it something to do? Is it a command to do something? You said Elizabeth says no. What about you, Richard?
I would say no, but I can see if like in a class setting you see solve or evaluate f of 2, why it would be to solve.
Okay. It doesn't say evaluate f of 2. It just says f of 2. Okay. So is it relevant? Does it have meaning if we don't do anything? This is the big question. Is it relevant? Does it have meaning? Is it useful if we don't do anything? If we don't plug 2 in and calculate it? The answer is absolutely yes. Okay? And that's what some of you were saying. So yeah, this is the value of the dependent variable of f, or the value of f, when the independent variable has a value of 2. It's no different than the g of 8.3 is what I'm getting at. But our students are trained. It's like, oh, where's my formula? Plug the 2 in, get the answer. Just like 11 or something. But it's the same thing. It's the value of the dependent variable of a function whose name is f, and the independent variable has a value of 2. Okay, so here's another good practice page. Given two quantities represented by y and p, suppose that p is a p is a function of y according to this function, capital Z of y equals 3y squared plus 8y minus 17. Where in the above statement do you see the function definition? We'll just do them one at a time. Where do you see the function definition? Where's the function definition? Is it the left side? Is it the right side? Is it? Whoa. Is that one of you guys?
Yeah, that was me.
What was?
Wait, you can see that?
Yeah. What were you answering by doing that? No, actually, it was the right answer.
No. I was trying to do the entire thing. I just wanted to see if that would work. Oops.
So what is the function definition? Draw it again. That's the right answer. It's the whole thing. The whole thing. Everything here is the function. Defining a function with its name and defining what values of the dependent variable are for values of the independent variable. That's the whole thing. Okay? Where do you see the dependent variable in this statement? Capital Z? So is it the left side or is it just Z? That's two different things. Okay, so just the Z. What do we think? Is that the value of the dependent variable, just the Z?
Oh, wait, no. Never mind. It's the Z of Y.
Z of Y, right? Z of Y. Okay? The dependent variable. Independent variable? Y, right? Y. Okay. Function name? Z. Function notation? Z of Y. Function rule? The right side is called the rule. Okay. The value of P. Where do you see the value of P in this? So there's, in the setup, right, so two quantities, y and p. P is a function of y according to this definition. Where do you see the value of P? Ashley, what do you think? Z of y? Okay, Z of y, the value of P. Anything else, the value of P? Entire right side. The rule, right? The rule gives us the value of P as well. That's why they're equal, right? So the value of P is either side. Either side gives the value of P. Is capital Z equals 3 a valid statement? Is that a valid statement? No, Z is just a name. It doesn't take on values. What was the intention of this? So rewrite the statement for probably what its intention was. Yasra, what do you think? Z of y equals 3, right? Z of y equals 3. And I said in two other ways. So z of y equals 3. What's another way that p equals 3? P equals 3 would also be right. Is there another way to write it? The whole right side equals 3, right? So yeah, probably by saying z equals 3, the person is intending that the dependent variable is 3. So that's z of y, or p, or the right side. Okay, quickly here. So in your homework, does this look familiar? These formulas look familiar from your homework? So there's the payment formula. This is a formula. And there's a payment function definition. Are they the same or are they different? The second one's more useful, so different in use. So why? Why do you say it's more useful? Okay. Right, so if I want, so my rate is 5%. My principal is $100,000, and I want my standard 30-year loan. I can represent that with function notation. This represents what? The monthly payment when the interest rate is 5% for a $100,000 loan and at 30 years, 360 months. How would I represent, how could I represent that with the payment formula? What would I have to do to represent that same value of a monthly payment? Using the formula, what would I have to do to represent with the formula? Could I? Okay. So one way would be, it would be 4 statements. Is there a way I could represent that value with just one statement? What would I have to do? But yeah, so that would be one way, and that certainly would not be efficient or convenient, right? So is there another way to represent that monthly payment for those values? What's that? Exactly. Right. I think I did this. I think my thing is still running, and that's so here's the kind of a different scenario. So here's for a 6.25%, 175,000 loan, 15 years. Here's how you represent that with function notation. Here's how you have to represent that with the formula. So now, obviously, much longer. What if I had a formula for my budget? I'm looking at buying different houses with different mortgage scenarios, and I have a big complicated formula for my budget. Which one of these is going to be more convenient to use in my budget formula? Second one, of course, right? It's concise, it's compact. It tells us exactly what we know. It's going to be the estimated value of my payment for these 3 values of the parameters. This is huge and clunky and will make my budget formula explode, right? Or make it big and yeah. So this is one advantage, and there's more, but this is one advantage to a function over a formula. Function notation is very concise. It gives us all the information, right? Easy to use in other formulas or other functions. Function notation is kind of the most convenient, as opposed to writing out this over and over again. Okay, so that's all we got time for.